So here's the first test in the Regents physics practice tests, the booklet from May 2023. So begin at the beginning. Vector. Vector mnemonic is MAD5. There's all the vectors. So scalar, all energy and work scalar, speed scalar, weight is the force due to gravity. All right, next. So for number 2, I wrote down all the given information. But it's asking about the mass. Mass doesn't change. Mass is the same everywhere. So if it was 65 kilograms on Earth, it's 65 kilograms on the moon. But be careful. The units are going to be in kilograms. It's the same mass, not the same weight. So I immediately knocked out 3 and 4. But for if it's the same mass, 65 kilograms is the mass of that astronaut. It is going to be the same mass on the moon. Number 3, sum of all the forces. That has a special name. Sum of all the forces is the net force, otherwise known as sigma F. But depending on who's listening to this, that may make sense or not. For the Regents people, sum of all the forces is F net. And it says if the F net is 0, if your sum of the forces is 0, your net force is 0, then your acceleration is 0, your velocity is constant, and you are in equilibrium. So if you are not accelerating, then you must be accelerating? No. Maybe slowing down? No, I am not accelerating. Slowing down is a form of acceleration, so definitely not 3. But if your net force is 0, it means you're not accelerating. And the reason why that's true, by the way, is because of Newton's second law, A equals F net over m. If there's no net force, then there's no acceleration. But you could be moving, you just can't be speeding up or slowing down or changing direction. So you don't have to be at rest. You may be moving at a constant speed. Okay, number 4. So in number 4, I'm looking at, I see the vocabulary term inertia. And it's talking about inertia of an object. And so how would you increase the inertia of an object? So let's recall that inertia is mass. And there's nothing else to that. It has nothing to do with motion. Inertia is mass. And so if I want to increase the inertia, I want to increase the mass. So increase the inertia would be done by increasing the mass. Not the net force, not the time, not the speed. Inertia is mass. So we increase the mass. Choice 1. All right, number 5, we have a number of givens. I don't know that we'll need all the givens, but I'll write the givens anyway. So we're told that we have a 100 kilogram cart and it's accelerating at 0.5 meters per second squared west. Sorry, I forgot to write that. West. And then as a horse puts a force of 60 newtons west in the same direction as the acceleration on the cart. What is the force that the cart exerts back on the horse? So we know of the force of the horse on the cart. And it's asking about the force of the cart back on the horse. So this is Newton's third law, where if you have two objects A and B, the force of A on B is equal to, and in opposite direction of, the force of B back on A. So if the horse puts 60 newtons on the cart is going to put 60 newtons right back on the horse, so that is choice 3. And then you could say, oh, well, if the forces are equal, why don't they cancel? They would only cancel if they were on the same object. These are two separate forces on two separate objects. 60 newtons on the cart, 60 newtons on the horse. And the reason why the cart moves and the horse doesn't is because the cart has less rolling friction. There's like wheels there, so there's like rolling friction there. Meanwhile, the horse is dug into the ground. But if it was really slippery ground, then yeah. And if it's like, suppose it was really slippery ground and a really heavy cart, then the horse would be slipping all over the place and the cart wouldn't go anywhere. So why would the horse be slipping all over the place if there weren't a force on it? So yeah, there's forces on both of them. They're equal and opposite. Third law. All right, next. All right, last one in this column, we're talking about sound waves. And sound waves are longitudinal waves, not transverse waves, so we can get rid of 1 and 3. Yeah, the transverse wave. So yeah, sound is not a transverse wave. Transverse waves are like doing the wave in a baseball stadium, or light is another good example of a transverse wave. So like electromagnetic and transverse, that is light, not sound, right there. And longitudinal, the particles vibrate in the direction of motion. So you have your compressions, and then you have your rarefactions right there, and they'll compress and rarefact as they move forward. Not a lot of examples of that, but sound is one of them. So it's like, okay, fine. So it's a longitudinal wave, but is it mechanical or electromagnetic? Well, electromagnetic is light, and we know that light is transverse, so it's not choice 4, it's choice 2. Now, what the heck does mechanical mean? Mechanical, whenever you see that, that means motion. And a longitudinal wave does move the medium that it's in, whereas light does not. So that those actual compressions and rarefactions in the medium are actual movements of that medium. So sound waves are mechanical and they are longitudinal. Choice 2. Okay, yippee, we did one column of problems. Now let's go to the next column and start with number 7. So in 7, I have an electrostatic force, 8 times 10 to the negative 5 newtons between 2-point charges Q1 and Q2. And it says the distance between the charges is doubled. We have a change word being double, triple, half, quarter. It says, what's the new electrical force? So we're dealing with electrical force, so that would mean Coulomb's law. And we're dealing with a proportional expression, so we're dealing with doubled. So I'm going to take the Coulomb's law and put it into like a proportion mode. I'm going to get rid of the constant, so that if I take all the variables and replace them with 1 and change nothing, then nothing happens. But it says the distance between the two charges was doubled. So the actual amounts of the charges stay the same, but it says that the separation was doubled. So 1 times 1 over 2 squared is a quarter. So it's not 1/4, it's not 0.25 newtons, it's a quarter of what the force was. So the force was 8 times 10 to the negative 5. And so a quarter of 8 times 10 to the negative 5 is 2 times 10 to the negative 5. And so that gets us choice 2. Another thing you can consider is that as if you increase the distance, the force is going to decrease. So I'm going to have a smaller force. So that eliminates choices 1 and 3. 10 to the negative 4 is larger than 10 to the negative 5. But just be careful with number 4. You could say, oh, 4 times 10 to the negative 5 is half of 8 times 10 to the negative 5. But don't forget that r is squared. So it's not 1/2 the electrical force, it's 1/2 squared, it's a quarter. So that's 2 times 10 to the negative 5, not 4 times 10 to the negative 5. All right, so that's number 7. Then number 8. So we have a blue lab cart going west when it collides with and sticks to a red cart traveling east, and they are both traveling. The magnitude of the momentum of the blue cart before the collision is 2 kilogram meters per second, and the red cart magnitude, and magnitude means amount. Remember that. Magnitude. Amount. So that's just a scalar, it doesn't concern itself with direction. So the blue cart was 2 kilogram meters per second, and the momentum of the red cart is 3 kilogram meters per second. What is the total momentum of the two carts after they collide? Alright, so the blue cart's going west and the red cart's going east. I find that with problems like this, it's good to draw a picture. Alright, so we're going to have a head-on collision because I have a blue cart going west and a red cart going east. And then it says, what's the total momentum after the collision? Well, let's remember from momentum that total momentum before is total momentum after. So we don't know anything about after the collision, but we know we can figure out the total momentum before the collision, and it's going to be the same after the collision. So total momentum before, so when you add up the momentums, we get 3 kilogram meters per second plus negative 2 kilogram meters per second gets me 1 kilogram meter per second. Now the negative on the blue guy is because it was going west. Direction totally matters. Direction really, really matters when it comes to momentum. That's worth noting. So, so yeah, if you, for this question, if you got choice 4, 5 kilogram meters per second, because you were just 3 plus 2, don't feel bad because you got the right idea. That is the total momentum. But direction matters. So it's not 3 plus 2, it's 3 plus negative 2, aka 3 minus 2, which is 1 kilogram meter per second. Okay, here we go with number 9. There's a lot of shenanigans happening in the class. So we have someone throwing something through the air, and it says at point P, which way does friction act? This looks really complicated, but you got to remember maybe 2 things here. First of all, friction always opposes motion. Even like when we use friction to move, like with car tires or with shoes, like when you walk forward, your foot is actually pushing backwards. And so your foot wants to slide backwards, but friction stops that slide, and it's actually the friction that's pushing you forward. Same principle with car tires. And like the car tries, pushes off of the ground with friction, and that pushes the car forward. But anyway, so friction opposes motion. It will always be in the opposite direction from the velocity. So it's like, okay, fine, but which way is the velocity? Well, for the projectile, this is like kind of like a projectile at point P, right? So we have at point P, the direction of the velocity there is straight forwards. It's moving that way. At this point here, it's going to be going that way towards the ground, and at this point here, it's going that way towards the ground, and up here at the highest point, we know that it's straight forward. All right, that's the direction of the velocity, but at point P, the direction of the velocity is straight forwards. But it's not asking what's the direction of the velocity, it's asking what's the direction of the friction force, which is opposing the velocity. There's the friction. So the direction for friction would therefore be choice 2. Look at this, we're almost done with the first page. All right, so magnetic field will be produced by a beam of what? Well, you got to realize where the heck does magnetism come from? So magnetism comes from moving electric charges. So you need to have electric charges. Neutrons are particles, but they are neutral. They don't have electric charge. Gamma rays and X-rays are both forms of light. So light photon, X-ray photon, they're both forms of light. Light is neutral. They're not even particles. They don't have no mass. They're photons. So by process of elimination, I'm left with protons. But a beam means that they are moving, and protons are positively charged, P positive. So a beam of protons would totally be magnetic. In fact, that's how they're easily controlled, because as they move, they're magnetic, and magnets can control the beam. So that is choice 3. Congratulations, that's the first page, numbers 1 through 10. We have a lot more to go, so let's proceed. Page 2, let's look at number 11. All right, so here we have 2 objects, A and B. It says the electric field, so this is an electric field that we're dealing with here, of 2 small charged spheres. So this is an electric field. And it wants to know what are the charges of A and B. So for 11, we have the electric field, and what the lines show is the path a loose, free to move, positively charged particle would follow in the field. So if you dropped a loose positive charge in there, what would it do? It would be repelled from positive and attracted to negative. So the path lines, the electric field lines go from positive to negative. So I can see that all of these arrows are pointing inwards towards A and B, so they cannot be positive. Ding, ding. And they must both be negative. And so yeah, 11 is 3. Number 12. So looks like the work done on the box. Let's write down the things that we know. I know that we have, give me the direction of the force as well. We have a 20 Newton pushing force is acting on a box that's 10 kilograms of mass. It displaces 5 meters to the east, and it wants to know what is the work done. Work we know is FD, where F and D need to be in the same direction, or components thereof. I do see that the force and the displacement are both east, so I'll just multiply them up. And 20 times 5 is 100, so 12 is choice 2. So for 13, we have a block initially at rest and there's no friction. It's also not on a ramp. It says horizontal surface. Then we have a pushing force of 5 newtons and it says 15 joules of work are done. And it wants to know what's the kinetic energy. So, well, kinetic energy is 1/2 mv squared. And except I don't know the mass of the box. And I really can't get V final without how far it went or how much time. And also I have no idea what the acceleration is. This will totally not work. So if that doesn't work, let's remember that by conservation of energy, the energy that is gained by the block is equal to the work that's done. And we're on a horizontal surface, so there's no change in gravitational potential energy. And there are no springs, so there's no change in spring potential energy. But it does speed up. It's being accelerated by the force. So the speed is increasing. And so that work that's done, that 15 joules of work that's done, that goes entirely to kinetic energy. And so 13 is choice 2, 15 joules. And we're at the bottom of this column. So number 14, A and B are held a meter above the ground. Mass of B is twice as that as of A. If PT is gravitational potential energy of A, what's the gravitational potential energy of B? I feel like I'd like a picture here. So two masses, A and B. B is twice as massive. They're both a meter above the ground. And it's asking about gravitational potential energy, which we know is mgh. And so they have the same height above the ground. They're both at 1 meter. But it says let's see, it's asking about B relative to A. B relative to A, and B is twice as massive. So if you have more mass, you have more gravitational potential energy because they're directly proportional. And so B, which has twice the mass, it's going to have twice the gravitational potential energy. And so that's choice 2. All right, let's go to the top of the next column. This one's pretty straightforward. Kinetic energy. We have the mass and we have the speed. Don't forget to square the speed. So, like I said, don't forget to square the speed. Don't forget the 1/2 either. And then when you round for 2 significant figures, we get 2200 joules, which is choice 3. Again, you're not held to significant figures on your shown work for B2 and C, but they will use significant figures for their answers. So if you want the precise correct answer, you have to pay attention to significant figures. All right. Anyway, number 16. All right, so we have frequency of a wave that's 5.09 times 10 to the 14 hertz. If you have a good memory, you may remember that is the reference frequency for the index of refraction chart. That would be like a yellowish-orange light. Anyway, so it says, speaking of light, electromagnetic wave is otherwise known as light. So we're talking about light here. In a transparent medium, the main factor that determines the speed of this wave. So if we're talking about a light in a transparent medium, what they're getting at is the index of refraction. N is C over V. And so determining the speed of the wave. Well, the amplitude of the wave is the energy of the wave, and energy is not related to speed, so that's not it. And the speed has no relation to the phase, whether it's in phase or out of phase, nor the distance, but the index of refraction is all about the nature of the medium, which is choice 1. And actually, I feel like them talking about light is a little bit of a distractor. It makes this question a little bit harder because it's not just light, it's any wave. Speed of any wave. Speed of any wave depends only on its medium. So yeah, 16 is choice 1. Then number 17. All right, so 17, they give the work, the time. The mass is 12 kilograms, and they say they're lifting. So if they asked for a force, if you had to deal with a force, you would get the weight of the object you're lifting. Whenever you're lifting something, the force that you're exerting is the weight of that object. We're not going to need the force for this question, but I'm just saying. And then they are asking for power. So we know that P equals mv. Oh, that's momentum. That's not the one you want. We're asking for power. Don't confuse your p's. Power is work over time. I know the work is 480 joules. I know the time is 5 seconds. So my power is going to be 96 watts, choice 3. Pretty straightforward. Next question. Talk about lifting something. Here we have an elevator lifting 2100 newtons. So it wants to know the speed that it can lift that at. So I know the power is 5.8 times 10 to the 4 watts. That's 58,000 watts. I know the weight of what it can lift is 2.1 times 10 to the 4 newtons. And it wants to know what's the speed that it can lift at. Here's another power equation, but instead of W over T, we also know that power is force times average speed. And so we know the force is 2.1 times 10 to the 4 newtons. Oh, hold on, I miswrote that. P is FV, but let me write it this way. So we have 5.8 times 10 to the 4 watts is equal to 2.1 times 10 to the 4 newtons times the speed. So when we solve for the speed, divide both sides by 2.1. Here, let's give myself a little bit more room. Divide both sides by 2.1 times 10 to the 4. We wind up with a speed of, we get a speed of 2.8 meters per second. That would be choice 3. And I wanted to finish this column before the end of the period, but you heard the bell. So I'm going to have to come back later for number 19. And we're back. So 19, we have a police officer with radio waves by radar gun. And they're hitting a vehicle, and it's going to be, compared to the emitted radio waves, the radio waves reflected from the vehicle and received by the radar gun. I'm looking for like keywords or whatever that says this is Doppler effect, and you can see like police officer is not moving, stationary police officer not moving. We have radio waves by a radar gun. And then it says you're comparing the emitted radio waves, so that would be the source of the waves, and then reflected by the radar gun, and so that and received by the radar gun, that would be the observer, and it wants to know about what would be different. So the speed's definitely not going to change, because the speed of the wave depends on the medium that it's in, and it's all in air. So the medium hasn't changed, so the speed won't change. But the wavelength and the frequency could change. So let's kind of look over here and talk about Doppler effect. And so if the source is moving this way, that's the velocity of the source, then what happens is that the waves that the source is making tend to bunch up in the front and spread out in the back. So this would be moving from this side, moving away from this side, and this is approaching on this side. So the speed stays the same, but if the waves are bunching up, then they're going to have a shorter wavelength because the waves kind of stack up. And since v is f lambda, and v is the same, then if v is the same and lambda decreases, then the frequency increases because f and lambda are inversely proportional. So if a source is an approaching observer, there's a higher frequency and a shorter wavelength. If they're moving away from the observer, then there is a lower frequency and a longer wavelength. So let's see what the answer choices are. So it says the cop is stationary and then the vehicle is moving towards the officer. So that would be approaching, and that would mean higher frequency and shorter wavelength. So we don't have a longer wavelength, it's going to be a shorter wavelength, and we do have a higher frequency. And period is related to frequency by t equals 1 over f, but if frequency is going up, then the period would be going down, so it's not longer period either. All right, then we have number 20. Light wave strikes the moon, reflects back towards the earth. It would be kind of like a laser or something. And as the light wave travels from the moon towards the earth, what does it carry? Any wave, light wave, any kind of wave, carries energy only. It does not carry material. I don't know what it would carry from the moon. Like what? Moon rocks? Like that doesn't even make sense. So what even would it carry from the moon? But that doesn't matter anyway. All waves, like this wave, all to cross out the all waves carry energy only. That's just a fact about waves. They do not transfer matter. But they do transfer energy, by the way. Now, standing waves actually don't transfer energy. They have energy, but they don't go anywhere. They're standing waves. So since standing waves are not moving, they don't transfer energy, right? And then you could say, well, a standing wave is in an instrument like a guitar or like a clarinet. How do we hear the sound if the energy doesn't transfer? That standing wave then turns into sound, and the sound then travels as a traveling wave. But anyway, that's just standing waves. This one is definitely a traveling wave. It's traveling from the moon towards the earth, so it is carrying energy along with it. All right. Then number 21. Time required to produce one cycle of a wave. That is the definition of period. The time for one cycle. Not much more to say about that. Next. I think what I'm going to do is make one video just for the multiple choice and then make a second video for the extended response, because already we're almost up on 30 minutes. All right, magnet question. So this is interesting. It says you have a compass placed near a copper wire. Wire is connected to a battery, current's created, compass needle moves, changes position. Why does that happen? And so basically the one thing that I noticed here, we're talking about magnetism, and it says a current is created. And it's important to remember magnetism comes from moving electric charge, and a current is moving electric charge. So the copper wire itself becomes magnetic. It develops a magnetic field. Now, be careful. It says the copper wire magnetizes the compass needle. The compass needle is already magnetized, because remember what a compass is. So a compass is a magnet that is free to turn and change its direction. So the compass needle is already magnetized, so it's not choice 1. And then it says the compass needle magnetizes the copper wire. It's like, no, like the compass needle is not that strong, and copper wire doesn't get magnetic anyway, unless it's carrying a current, and that's not the wire that's magnetic, it's actually the moving charges that are magnetic, so not this guy. Insulation of the wire becomes charged and exerts a force on the compass needle. I don't know how the insulation would become electrostatically charged, but choice 4, the current in the wire produces a magnetic field because it's moving charges, and that exerts a force on the compass needle. That is true. Okay, so here we have a calculation question. We have monochromatic light with that frequency. That's the reference frequency for the index of refraction chart. And then it says has a wavelength of 589 nanometers in air. What is the wavelength in lucite? And you don't actually have to worry about converting away from nanometers. Nanometers are 10 to the negative 9 nano, but all of the answers are also in nanometers. So we can kind of leave the nanometers alone. And so we're comparing two different indices, air and lucite, in two different wavelengths. So lucite, we can look up on page 2 of the reference tables. Page 2 of the reference tables. And we have, that's why we have this reference frequency here, because you'll find that on the reference table too. The lucite has an index of 1.5. And so, and in air you should know has an index of 1.0, but if you didn't know that, that's also on the index of refraction chart. And so we have N2 being lucite, 1.5 over N1, which is air, and then lambda 1 for the air, that's 589 nanometers, and I'm looking for lambda 2. So when I cross multiply, I wind up with 589 over 1.5, and I get, and we wind up with a lambda 2 of 393 nanometers, and there you go. Another way you could have solved this problem was done n equals c over v using lucite to get the speed of light in lucite, and then done v equals f lambda, given that frequency to solve for lambda. You get the same answer, 393 nanometers. All right, next question. Increase the amplitude of a sound wave. What does that also increase? That would be the loudness, because the amplitude of a sound wave is its energy. And so it's related to the energy of the wave. So if you increase the energy, you're going to have a louder sound. Pitch is frequency. So if they said they increased the frequency, then they would increase the pitch. But they did not say that. All right. And so there you go. Yeah, and if you wanted to increase the sound's velocity, you would have to have it in a different medium. Okay, we have 25 at the bottom of this column. We have a nice parallel plate setup for the oppositely charged parallel plates. Probably something about electric field. Let's see. Point P is located in the electric field between two oppositely charged parallel plates. Compared to the magnitude and direction of the force on an electron placed at P, electrostatic force on a proton placed at P is what? So let's compare the electron and the proton. So the electron and the proton, they are both one elementary charge. The proton's positive, the electron's negative, but they have the same elementary charge. And however, proton's positive and electron's negative, and we know that all electric fields, and then we know from number 11 that the electric field show the path a loose positive charge would follow in that field, which is away from positive and towards negative. So this electric field is going to be doing like this, from positive to negative. And that's, so the proton would move towards the bottom plate, but the electron, which is negative, would be repelled from the bottom plate and attracted to the top plate, because opposites attract. Opposites attract. Opposites attract. All right. So let's see. Compared to the magnitude and direction of the force on electron, the proton would have the same amount of force, because E is F over Q. So if you're going to have the same electric field and the same charge, you're going to have the same force. So it's going to have the same magnitude of the force. So not 3 and not 4. But the proton would be attracted to the bottom plate, whereas the electron would be attracted to the top plate. So the force would have the same magnitude, but it would be in the opposite direction. There we go. All right, next column. We're getting close to the end of part A, the first 35 questions. All right, 26. Two or more sound waves pass through the same point, and when they're passing through the same point, they interfere with each other. Diffraction is when you wrap around a barrier. You basically go through a barrier, and the wave wraps around and changes direction. Refraction is when a light wave, usually it doesn't have to be a light wave, when a wave goes from one medium into another medium at an angle, and if its speed changes, then its direction changes. And then resonance is when you have two objects that vibrate at the same frequency. If like one object hits the other object at its natural frequency, it'll not just vibrate, but the amplitude of that vibration will increase. But when you have two waves passing through the same point simultaneously, they will interfere with each other. So 26 is 1. That's the definition of interference. Okay. I'm going to break here. I'll come back later. Okay, 27. We've got two photons, gamma rays and microwaves. And they're in a vacuum, that's like space, compared to wavelength and energy of the gamma ray photon. What is true of the microwave photon? So, referring to the electromagnetic spectrum, which electromagnetic means light. Okay, so the way the EM spectrum is structured on the reference table is on the left side they have the short wavelength, the low wavelength, and high frequency light, and then over on the right side they have the long wavelength and low frequency light, and then in the middle there's like a little small portion in the middle which is the visible light, which is just a small chunk of it. But microwaves, and you can this is on page 2 of the ref tabs, this table, the electromagnetic spectrum chart, and your microwaves would be somewhere around like not as long wavelength as radio waves, but it is definitely lower frequency and longer wavelength than visible and infrared. So like kind of like microwaves would be like there on the spectrum. And yeah, if I actually look at the reference table, the frequency for microwaves is somewhere from like 10 to the 8 to 10 to the 12 hertz. But then gamma rays are all the way on this end. They are super high energy, gamma rays, gamma. And then gamma is coming in with a frequency starting at about 10 to the 18 and up. So the frequency is greater than or equal to, or well, greater than, not really equal to, greater than 10 to the 18 hertz. All right. And then it says, so comparing the two, the microwave photon as compared to the gamma rays, microwave has a lower frequency, relative to gamma rays, and since F and lambda are inversely proportional, it would have a higher wavelength, a longer wavelength as well. And then it refers to the energy. We know that the energy of a photon is given by HF. Energy is also given by HC over lambda. But in either case, the lower frequency of microwaves means that it's lower energy. Longer wavelength also means lower energy. So as compared to gamma rays, microwaves are going to have a longer wavelength, ding ding, and less energy because they are lower frequencies. So that's choice 3. Standard model, it's the last topic we do. It says look up neutrinos. Neutrino is a type of what? Standard model. The chart of that stuff is on page 3 of the ref tab. And so we're looking for neutrinos on the standard model, and neutrinos show up only once on the page, and that's down at the bottom right. And those neutrinos are included with the leptons, which is choice 1. Leptons you cannot find them in the nucleus. They do not interact through nuclear strong, so they'll never be in the nucleus. Famous example of a lepton is the electron. Now, photon is a photon of light that has no mass, so neutrino is not a photon. Photon would be light, so not two. And then a meson is a quark and an antiquark, and a baryon is three quarks. And I can see that that's given on the bottom left page, the bottom left corner of page 3. And so it's not meson, it's not a baryon, it is definitely a lepton because it says it on the ref tab. It just says it straight up right there. Speaking of baryons, I want to produce a neutral baryon. And so I'm still on page 3 of the ref tabs. But I'm looking at the quark chart, which is about middle right on the page. Quark chart. Middle right of that page has the chart of quarks. And so we have CTS, DSB, UDS, and UCT. These are all abbreviations for quarks. And so CTS is charm top strange. DSB is down strange bottom. 3 is UDS is up down strange, and then 4 is up charm top. And each one of these quarks has a fractional charge. So let's work out what they are. And so charm and top are both plus 2/3 E. Strange is negative 1/3 E. Throw it all together, you get positive 3/3, which is plus 1. That is a legal particle. It does come out to a whole number of elementary charges, but it is not neutral. I said which one is neutral, so that is not it. Then down strange bottom. That's also a legal particle. We have down is negative 1/3, strange is negative 1/3, and bottom is also negative 1/3. Throw that all together, we get negative 3/3 E, which is negative 1 E, which is a legit particle, just not neutral. And then baryons, by the way, have to be, we'll finish this question. Baryons have to be 3 quarks. A meson is a quark and an antiquark, but all answer choices are 3 quarks. So let's keep working this through. We have up, down, strange. That sounds promising. I think that's the answer, so I want to do choice 4 first to show how it's not the answer. So up is plus 2/3. Charm is also plus 2/3. And then top is also plus 2/3. And that gets us plus 6/3, which is plus 2 elementary charges. Also not neutral. So by process of elimination, it's choice 3, but let's find out why. Up, plus 2/3. Down, negative 1/3. Strange, negative 1/3. And so what that gives me is 0 elementary charges. The answer is choice 3. Okay, number 30, they give us mass and they want the energy. How much energy is released? This is just an E equals mc squared question. The speed of light is found on page 1 of the reference tables, and don't forget to square it. And so we wind up with 18 joules, which is choice 2. All right, number 31. So you hit a ball straight up. If you hit a ball straight up, that acts like free fall. We are slowing down under gravity. So we know V initial is 28 meters per second. V final is 0 at the highest point, but I don't know that it gets to the highest point. I do know the time, and I know the acceleration is negative 9.81 meters per second squared. So they give us V initial, they give us the time. We know that it's rising under gravity, so we know the acceleration is due to gravity, negative 9.81 meters per second squared, and we're solving for Vf. That's 28 plus negative 9.81 times 2.2. It's still on its way up. We get a V final of 6.4 meters per second. Slower than 28, but still positive, still on its way up. So 31 is 2. Then 32. We have elementary charges and voltage, and it wants the electrical potential energy, the energy of the particle. Now, charge, we usually require charge to be in coulombs, so we would need to convert. But before we convert, let's keep writing things down. Voltage is 4.5 volts. And they're looking for electrical potential energy. When we're talking about electricity and energy, they like to use work instead of energy. So it's asking what is the work, and of course the formula that relates the three, V equals W over Q. Now again, if I have charge in coulombs, then I need energy in joules. But all of the energies, notice, they're all in electron volts. So if my energies are in electron volts, I can leave the charge in elementary charges. We got 13.5 eV, choice 4. Okay, we're almost done with part A. So here we have series and parallel circuits, and I want the largest equivalent resistance. So in a series circuit, the resistors simply add up, but in parallel, we have the reciprocal equation. And so the series circuits are 1 and 3. These guys are series because they all connect in one loop, but 2 and 4 are parallel because they're connected in parallel branches. Well, I can tell you that connecting in series, as you add resistors in series, it's always going to be more than adding resistors in parallel, but be careful, the numbers are different. So let's see what we get. Series is going to be easy. We simply add them up, and for choice 1, 2, 2, and 4 makes 8 ohms altogether. And then for number 3, we have 2, 2, and 6. That makes 10 ohms altogether. That's the winner so far. And then for parallel, I have 1 over 2 and 1 over 2 and 1 over 4. So there we have it. Yeah, I figured there would be. The parallel circuits have lower resistance than the series. They usually do. So the largest equivalent resistance would be this series circuit here, choice 3. All right, we are almost done with our part A questions. So we have a transverse wave right here, and since it's transverse, I know that if the direction of the wave motions to the right, then the particle is going to move up and down. So it's not going to be 1 and it's not going to be 2. So that particle x is either going to be going up or it's going to be going down. So the way we tell is at the next instant in time, if the wave is moving to the right, what is on its way? Is the crest on its way or is the trough on its way? And if I shift that wave to the right, I'm sorry. I circled those things correctly, but I called them the wrong things. Is the trough coming in or is the crest coming in? And if that wave is moving to the right, it's the crest that is coming, and so x is on its way up. If the wave were moving to the left, if this one is going to the left, then the trough would be coming and x would be on its way down. But that's not the case. And so we have choice 3. And then finally we have our magnetic fields, remembering that. Magnetic fields, they show the direction a compass would point in the field, and now it's towards south and away from north. And so for the first one, we have away from north on the left, but not on the right, so no. Then for choice 2, we have away from north on the right, but going into north on the left. No. Then we have choice 3, going into north on both sides. Double no. But choice 4, coming out of north, away from north on both sides for both norths. Yup, that's my answer. Now, I'm now at 49 minutes on this video. I was hoping to split the Regents into 2, do the multiple choice, and then the extended response. But I think instead I'll do part A, then B1 and B2, and then C, and do it in 3 videos. So see you next time for video 2 of 3 on these solutions.